Hello, my name is Jonathan Kenny. I'm a member of Team 58, and our two projects are ink degradation and tire analysis. Going into a bit more of what they are, ink age analysis, which will be our primary focus throughout this presentation, is covering the research we've done and the testing on developing a way to determine the age of something based on the printer ink decay. This is done using colorimetric data from color filters and calculating ink age based on a spectrometer's readings. Additionally, the second project that we'll be undertaking is the tire pattern analysis, which will be using a tire and camera mount along with tread scanning to then be putting it into a computer system where it can use preconceptual computing to analyze the tire pattern and treads and mark out any key indicators. Before we get into everything, I'll give you a quick introduction of the team that we have. So starting from the left, we have Camille Imbler. She's a mechanical engineering technology senior here at Purdue University. Nathan Miller, an electrical engineering technology major, also a senior here, and myself, who is an electrical engineering technology major as well.
For the problem description for our project, we have two parts. We have the ink analysis and the tire impressions. For the ink, we'd like to determine if the document had been altered. This would be fraud. And then hopefully accurately estimate the timeline of an altered document using several different methods. For the tire impressions, we'd like to create a tire and a camera mount to analyze tire patterns, which can tell you the service history, speed the tire is going at. And both of these parts of the project would be very heavy in forensic applications. For the scope of work, we would be using two spectrometers and a spectrophotometer to collect some accurate data regarding the wavelength or the LAB values of these color values using colorimetric data. And as I said, using a spectrometer. So we have the Chinese one and a Pennsylvania-based one and the spectrophotometer. For the tire analysis, our project cost analysis is $50 for the turntable, $30 for the plywood, and $20 for a camera mount. And then we'd like to make sure that it can handle the 220-pound weight limit that's based off of the turntable, and then certain size considerations for variable tire size. And we're still waiting on that turntable to be delivered so we can go forward with that part of the project. For the state of the art, we're using spectroscopy. Unfortunately, this is a little bit expensive and it's not very mobile or easy to replace. And we'd like to do regression analysis. That's why we're collecting all of this data so that we can create a baseline using SEDs, which is standard erythritol doses. And then possibly going forward, we'll use a profilometer for depth gauge for the tire analysis.
For our system solution, these are our experiment setups. So on the left, we have the Theramino spectrometer software showing the dominant wavelength being read off of that, our gold buff paint sample. In that picture, obviously, it's not covered up with the box as it is shown in the middle picture. So in that middle picture, we're covering up with the box to block out excess light. We'll also be soon painting the inside of that box black so that excess light doesn't bounce around from our light source. That's just out of the cut off at the top of the picture there. And we'll also be looking to cover the box with something like a towel to block out any excess light. And on the far right, we have the X-Rite spectrophotometer readings that we got from the red gumball paint sample. And using the X-Rite spectrophotometer is actually quite easy. Once the battery charges, you basically just push down on it, and it gives you a beep and says completed, and gives us our values. And it gives us LAB values, which are light, dark, red, green, and blue, yellow. So for results, these were done a little bit earlier in our testing. We printed out samples. We kept one original that was unaged, and we aged one with a 100-watt UVA light bulb. And shown below, we did actually get some difference in the wavelengths measured with our spectrometer. And for our more recent results, we used the same 100-watt UVA light bulb. We also used a 13-watt fluorescent bulb, and we used the 5 paint samples that are mentioned earlier. For the spectrophotometer, it gave very consistent readings as we saw in the last picture. And for the American spectrometer, we used different situations with the fluorescent bulb, the UVA light bulb, and a different stand for each one of them. So we were experimenting with different backgrounds for our testing, and we got significantly different results between the fluorescent and heat bulb, but we got pretty consistent between fluorescent bulbs even with different lampstands.
So going with the first setup that we have, this method is going for our spectrometer. In this demo, we're going to be using the American-made spectrometer that we've been given, along with the fluorescent light bulb. Additionally, over to the side, we have the UVA bulb that is what we used for our initial testing on the 2 slides previous. So when setting this up, we'll go ahead and just lift the box, move in the spectrometer, set the light on top, and then using a predetermined colored paint cards that we picked up from the store, set this on the edge in front of the box. Set it in front of the spectrometer, and then from there we'll record the data on the computer. So moving over to the computer, going off of the different peaks, using the highest peak, we'll be able to determine which the highest wavelength is, and that will be added into the data we record for this.
This is our spectrophotometer from 2007, gifted to us by Dr. Steele. As you can see, we have these calibration resources, green, blue, and then a light and a dark. If you come over here, we are given our LAB values. L correlates to the lightness, so 0 is light and 100 would be black. A is the red-green value, and then blue is blue-yellow. This is our previous reading, but I'll show you how to do it again, and you'll see how consistent it is. Yeah, so as you can see, it only moved by 1/100th of a value for L.